Okay, so I wanted to do a quick video on functions and inverse functions, and it'll be kind of a review of what we did in our most recent class, but I'm kind of excited because now I've figured out how to get Screencastify to work with the microphone that I attached to my headphones, and I have like a Bluetooth keyboard set, so like I really feel like I have got finally all my technology figured out, so I don't have to bend over backwards to get these videos uploaded on the web, and we'll see. But so when we talked about functions, the first thing we talk about is a function is like a rule, right? And it's a rule that assigns different numbers to other. Well, it doesn't have to assign numbers, but we always talk about numbers. So we're thinking of a function like a rule that's going to have certain numbers like inputs, and it's going to assign for each input different outputs. So like I could have, it takes 1 in and it spits out a 4, and it takes 3 in and it spits out a 6, and it takes 5 in and it spits out a 2. And that would be an example of a function. It's a rule that assigns for everything that's in the input, it assigns 1 and 1 and only 1 output. And what would you, I think the thing that you want to understand is what's not a function. I'm not saying that this is not a function, but what would an example of something that's not a function look like? Well, if I had, let's say, inputs like 2, 4, and 6, and I had an output like 1, and 2 spits out 1, and 4 spits out 1, and 6 spits out 1. This is not a function. This is not a function because there is not exactly one output for every input. Okay, so I think you understand that, and I think what also is important is saying that in our math speak, we move on from calling these inputs and outputs to domain and range. Okay, so with these things, the domain is the numbers that go in, and the range is the numbers that go out. And actually, now I think I have to correct myself, because now when I think of it, I think if 3 different numbers all output the same number, then that, yes, it is a function. What we wouldn't be allowed to have would be if I switch these, like if an inverse function is flipping the domain and the range. If I switch these and I had one input going to multiple outputs, now this is not a function. Okay, so we have to keep those clear in our head. And the purpose of this video is to talk about the inverse functions. So the inverse is when you switch the y and the x. And I think I'm going to move us from these circle egg maps to tables. And let's think of what I had for the example that I said, yes, it is a function, even though I messed up the first time. If it went from 2 to 1 and 4 to 1 and 6 to 1, and what would that look like on a graph? Well, here might be 2, and here's 4, and here's 6, and here might be 1. And if I now think of what would the inverse function of this look like, I'm going to do that thing and use that word that is one of my favorite words in the English language to say, and it means to switch to the place of two things, and the word is juxtapose. And I'm going to juxtapose the x and the y columns, and now I have 1, 2, 1, 4, and 1, 6. And when I graph these, now, I have 1 on the x-axis, 2, 4, and 6 on the y-axis. And if I look at that, what makes it not a function, what you guys are familiar with, is the vertical line test. And the vertical line test says that if I can draw a vertical line and it goes through more than one point, it's not a function. And I think oftentimes you remember the vertical line test, but forget why it's the actual rule. It's the rule because there are multiple x's going to the same. So there's one x going to multiple y's, and that's not okay. So if we think of, but I guess the other things is notice that the one that was a function, it was okay to be able to draw a horizontal line through it. But then when we took the inverse, that horizontal line that went through multiple points became a vertical line that went through multiple points. And let's think of an actual function with a mathematical rule, like y is equal to x squared. And we know this is going to form a parabola. And if I fill out the table like this, I get that. And if I think of the inverse function, it's, well, one way to think of the inverse function is on Desmos. So if I get y is equal to x squared, then I can on Desmos. Desmos lets me do this. Your graphing calculators won't let you do this, but this is kind of neat. I can just switch the y and the x's. So now I can write x is equal to y squared. It's not written where x is the function of y, which is what we usually like, but these two functions are inverses. And you can see that I could draw, let's say I could draw like a horizontal line at, what's it going to be at, x equals 2, or it's going to be at y equals 2. And not looking at the inverse function right now, it goes through multiple points. And if I was to now look at the inverse function instead of the original function, and I draw a line at, like, let's say y equals, nope, x equals 2, now it goes through multiple points on the inverse function, which makes it not a function. But what I could have done back when I started is I could have said, well, this is going to fail the horizontal line test, so I'm going to make a domain restriction, and I'm going to say x is greater than or equal to 0. And then when I graph the inverse function, so when I said x is greater than or equal to 0, I'm only getting half of that graph. When I graph the inverse function, now I'm getting more than half of the graph. So I'm going to need to make a restriction on this one, but it's not going to be the same. It's not going to be a domain restriction, because if I make the restriction x is greater than or equal to 0, well, this graph was already all in the side of the graph where x is greater than or equal to 0. The restriction that I want to make is y is greater than or equal to 0. And so I'm going to make a what was the domain restriction in one becomes the range restriction in the other. And now these things look like inverse functions. And one way you can think of inverse functions is folding it. And it's folding it along the line y is equal to x. And if you think kind of long and hard about it, the reason that it is like this is because we're juxtaposing the x and the y column. Okay, so if you take a number, a point on a graph, like let's say 4 comma 1, and you juxtapose the x and the y, you get 1 comma 4, and you're essentially jumping across that y is equal to x line. So if I'm looking at this function thinking what's wrong with it, well, I have -2, -1, 0, 1, and 2. Not that there's anything wrong with it, but there's something that's going to make it not a function. Oops. And if I draw these arrows here, I'm going to get multiple arrows going to the same y values. And if I think of the inverse function, which in this case, the inverse function is, if I were to find the inverse, I would get x is equal to y squared. And then if I were to square root it, I would get y is equal to the square root of x. But something strange happens in this. Like we've sort of defined in math, we've sort of just defined the square root of x to be the positive side. And I think we've done that because we want it to be a function, but technically the square roots can be either positive or negative. So you sort of should think of the inverse function looking like this, but we've already made the domain restriction. We've just done it so many times, we've gotten used to doing that. But if you remember, if I say square root of 25, a lot of people do just put 5, but technically the answer to the square root of 25 is 5 or negative 5. So if I were to think of what does the inverse function of this look like, it technically would look like 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2, which on one of these egg maps would look like, what would I have? I'd have 0, 1, and 4, and I would have -2, -1, 0, 1, and 2, and 0 would go to 0, and 1 would go to -1, but it would also go to 1, and 4 would go to -2, and 4 would also go to 2. And so that would be not a function, but we could restrict it. And I think I want to show you one more thing, which is kind of like, what is a typical problem that you might want to be able to do? And I've got this link that I'll share with you that has a whole bunch of these problems. Let's take the first example, and it says that given h of x is equal to 5 minus 9x, find the inverse function. And let's do that. Let's say h of x is equal to 5 minus 9x. And I think for me it's helpful to just replace the h of x with a 5 minus 9x, and then we're juxtaposing the x and the y, so I can just put the x where the y was, and I can put the y where the x is, and I get x is equal to 5 minus 9y. But in math, we never see the x as the dependent variable and the y as the independent variable. We always see it the other way, so I got to do some things algebraically to get y by itself. And I get y is equal to 5 minus x over 9, or if you're into this kind of thing, you could do it 5 over 9 minus x over 9. And then the final step before the final step is rewriting it, and rewriting it in the same notation that it was given. And so this -1 right here, when you read this aloud, you read, let's see if this works. I'm going to read h, then I'm going to read inverse of x. Okay, h inverse of x is equal to, and I'm just going to take that and I'm going to write 5 minus x over 9. And this is the prelude to the final step. I don't know if that's the right word, but there is actually one more step that I want to do, because I want to check if I actually did it right. And the way that I check if I actually did it right is understanding that the rule between two inverse functions is that they undo each other. So it's like a round trip ticket. If I took a round trip ticket, I don't know where I went to, but if I took the whole round trip, I would end up where I started. So if I do h of h inverse of x through function composition, I should be left with just x. And if I think of what is h of h inverse of x, well, it's taking this expression and it's plugging it in for the argument. The argument is what we call that thing inside the function of h of x. So when I do that, h of h inverse of x, that's going to be 5 minus 9 times something. And this something is going to be this expression right here, 5 minus x over 9. And now I have to do some work. And what's nice here is this 9 is going to cancel that 9 right there. So I get 5 minus the whole expression, 5 minus x. And then what I often see people forget is that when you have a minus in the whole quantity, you have to distribute that minus sign into both expressions or all expressions inside the quantity. So boom, 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 those are gone, and you're left with just x. And you might think, all right, I'm done. But if you wanted to be a little bit more thorough, if this were a test and we were in normal school, I might require that you be more thorough and that you show me that you've done this not only one way, h of h inverse of x, but I want you to show me the other way too, h inverse of h of x, which would equal, now I'm taking this one as my shell, and I'm plugging this expression in to the x in that function. So now it's going to be 5 minus something divided by 9. And inside that something goes 5 minus 9x. And if I simplify this, I'm going to have 5 minus 5 plus 9x divided by 9. The 5's cancel. I get 9 over 9x. The 9's cancel, and I'm left with just x. And then I'm done. And then I go back because I want to check, and I see if my solution is the same as the one that's on this website right here. And I can show all my steps. And boom, 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 boom. Looks like I got it.